watching the Aussie BIM Guru, and today we're going to run through the final part of my tutorial series in regards to solar responsive facades in Autodesk Revit and Dynamo. So if you've tuned in with the last few sessions, in the first part I went through how to process image files in Dynamo. So you'll see here an example of a script that I built that was able to basically simplify an image into smaller parts for use in other scripts. And in part 2 we looked at adaptive components. So we took a facade, in this case study, and we converted the panel to an adaptive component that was able to move, and then we applied that to a conceptual mass in Revit. So if you haven't seen these two sessions, I advise that you go back and view them before this one, because this will basically be a lead on from those sessions. So part 3 we're looking at today is a solar responsive facade. So we're going to make the facade move in principle. We're going to look at an alternative panel creation method first, which I mentioned in my last session, which is using a package called Lunchbox in Dynamo. So we'll just go over to Dynamo. So this is my version that I'm currently using for anyone that wants to follow along at home. And it's the latest build at the moment. So I've just set up a little script here which shows you an example of some of the nodes that are featured in the Lunchbox package. Lunchbox basically deals with how to tessellate surfaces, apply panels, and a few other complex functions. So most of the functions that I use in Lunchbox are under geometry panel, and there's a whole bunch of surface types you can use based on surfaces in Dynamo. So you can see here I've selected a few surfaces I've set up in my model. I've got 3 of them. One of them I'm applying a quad panel to, one I'm applying a triangular panel to, and one I'm applying a staggered quad panel to. I'll just turn off the preview for the surfaces so it's easy to see what happens. And I'm going to feed in a few families into these. So I'm just going to load in a couple of default Autodesk panels. So I'm just going to load in a triangular and a rectangular pattern. And I'll just use the flat surface triangle for this one, assuming the panels will be flat. I'm just going to quickly adjust the triangular panel because I know that out of the box this one has some issues. And I'm just going to go in and modify the surface and just regenerate a new face, because I know that the default template doesn't actually have those constrained by default, which is a bit strange, but it is what it is. And if I load that in, so to the triangular panel, I'll apply to the triangular pattern, and the rectangular pattern I'll apply to the rectangular panel. So you'll see here I've set up a UV grid. I've got 5 in the left to right direction, 3 in the vertical direction. I'm feeding those into these 3 panel definitions, taking the points and applying them to an adaptive components by point node. So if I run this, you'll see that it'll basically subdivide my surface for me, and it'll also apply adaptive components to those respective sets of points. So if I hide the form in this view, which is currently obscuring my panels, just move that. You see it's effectively applied panels across those as well. So instead of using conceptual massing, you could potentially use this as an alternative way to set up your framework. However, it does rely on regular UV spacing, which isn't always suitable for facades where you might have different heights between floors. But you can see this is an alternative method. But I'll move on to the main session for today, which is dealing with actually programming the facades. So we're going to look at one method to begin with, which is to use the brightness of an image to map how open or closed our panel is. And there's an alternative way of looking at it as well, which we won't do today, but it's possible, and that's to look at the hue, saturation, brightness values of those respective colors if it's not a black and white image you're processing, such as a thermal imaging diagram. So typically in HSB values, the hue indicates the temperature, blue being the coolest, green being the middle, and red being the hottest. And basically those colors come and go as you rise up the spectrum. So an example of a formula you could use is a heavily weighted formula on red, mid-weighted on green, lightly weighted on blue, divided by the total factor of weighting, which would give you a rough indication of how hot your temperature is on a scale of 0 to 1, which can be plugged into a facade panel after. But today we're going to be focusing on how bright a color is instead. So if I go into Dynamo, I'm just going to open up one of my masses from the last session. So you may recall this mass we were working with. You can see an example of what we're going to aim for here today. So I'm just going to tab select one of these panels so that I can reset the open value. So I'm just going to make them all 0.2. So I have to do select all entire project. And you recall that the panels are built such that they're either between 0.0 or 0.5 in terms of how open or closed they are. So ideally we're going to be mapping a range of values to this number in order to effectively achieve our open or closed ratio on our panels. So if I go back to Dynamo, which is not currently pointing at this document, I'll open up a script I've set up called Solar by Image. I could run through the script entirely in construction, but I think this probably takes a little bit too long. I'd rather run you through the methodology of how the script is set up and how the data is managed instead. So ultimately, this script is set up to collect all the curtain panels in the current view. You could do a selective selection if you had more curtain panels on your mass than what you wanted to act on. But for this case, I've taken the location of them all, I've taken the Z value of those points, and I've used list sort by another list in order to rearrange the order of those panels. Because by default, typically those panels will be arranged in the order of their ID by default, and that isn't always necessarily arranged in the way that we want to apply pixels of an image. So typically pixels of an image are mapped in rows, and then the column value is the order of how they sit in each respective row. The panels, not necessarily. So I'm sorting the list by the Z value, and then I'm taking that list, breaking it up into the number of rows, and then sorting those respective rows into their X value, in this case, so how far from left to right. There's a lot of methods you can use to rearrange curtain panels into the order you need, but typically X, Y, and Z will be the factors that you'll use. You could always draw a line as well and use that as a reference for how far along that line each panel is. But in this case, I've used that to rearrange the panels so that I can get rows, then columns in structure. So if I just disconnect this list here, and just run this formula, you'll see that this is my order of panels I'm getting at the end in order to apply my ratio of pixel from my image. And you can sort of see the sorting that I'm going through here in order to break them up into lists. They're quite complex nodes to work with, but in principle they take one list, rearrange that list, and then shuffle a list in the same format. So I'll reconnect that up to my elements at the end. So our destination is basically to take a value and map that to the open factor of each panel. You'll recall that the open factor parameter is the one down here that we've just reset, down here, and that's currently 0.2 for all panels, but we're going to map a range to that between 0 and 0.5. So the other side of this script is we're taking an image. In this case, I'm just going to browse, and let's just pick a left to right mask. So I've sized the images roughly to the aspect ratio of the facade overall. So I've mapped them roughly to 1500 by 500 in pixels in this case. And then I'm taking 15 panels in the left-right direction, 5 in the up-down direction, which is basically the number of panels in my system. There's not really a good way to detect that. Usually it's best to manually count and put in the formula yourself. If you were going to make it a Dynamo player script, you could make these inputs as well. And then I'm feeding these basically up here to chop the lists into rows, but I'm also using them to take that image and divide it into samples or pixel samples along that image. So I can basically pick at which moment in the image each panel should be corresponding to, because from there I'm taking the brightness of that image. I've set up another alternative option I'll show you, which literally randomizes the numbers. And I'm either going with half of that from 0 to 1 to map it to a 0 to 0.5 range, which is basically inversion where it will follow the sun. And the alternative is to do the opposite where it strays from the sun instead. So for now, we're just going to do the strays from sun. So that's basically 0 to 0.5, but the opposite of that. So 0.5 minus that, basically to flip the order of whether it's between 0 and 0.5. So I'm just going to run this script. They take a little bit to run at the moment. Keep in mind, this script is purely working off this image at the moment. There is a sun here I've added, but for this script, it's not actually doing anything. So you can see here, we've achieved the fall off along the facade. So basically, if I take my image file, you'll see that basically the wider it is in this case, the more open the facade is, and the blacker it is, the more closed the facade is in this case. So you can see those values have been pushed in to each panel respectively, depending on where they sit on that image. So you can see at 0.48, so it's almost closed in that case. You could alternatively take another image, such as this one here, which is quite pinched in the left to right direction. So basically it should be more open in the middle and more closed on the ends. And it will basically reapply that range to the facade, and you can see that occurring there. So you can see how quick and powerful this method can be, because you can have so many options. I could take, say, a focal point on the facade and sort of explode out from that point. And you can see just how strong this can be for a facade. And this is a very small scale facade. You could do this on a very large scale facade to get quite dynamic outcomes. So you can see there it's responding basically to that point of focus. So you can see there how the kinetic facades are folding up. So this is sort of the basic process I was aiming for in my first step of this. Now I'm going to show you two alternative methods. So another alternative method that's probably more popular for facades with the sun is to check either by angle or distance from the sun. So the first one we're going to do is just by distance, so purely how far away is an actor, which in this case will be the sun, to the panel itself. This one's quite simple to set up. It's a very small script, but it works in an entirely different manner. So I'm going to say no to save. So we're to solar by actor. And what I've done here is I've added a sun into my model. So it's basically just an adaptive component that I've hosted to a point. I should be able to see it in floor plan, I believe. Yes. And I've created a plane, which is basically the distance of the sun. If I go into 3D, again, I can take that point. I can laterally move it around to reposition the sun's location from there. So that gives me 3D control of that object. And that's basically our actor that will influence our facade. So if I go back to Dynamo, so this script is a lot more simple. It's taking the curtain panels, getting their location, getting the location of the sun. It's checking the distance at every single point of those panels to the sun, basically mapping those to find the largest possible item of that range, taking everything else away to normalize the range to a range of values that we can then turn into a percentage of their minimum possible value to their maximum. So where do they sit on the spectrum of those ranges of values? You could take a known minimum and maximum instead and just assume that some of your panels will be further in that range, but I prefer to do a normalized range where your lowest value becomes 0% and your highest value becomes 100. From there, again, we've got the same options. You can either go away or with the sun. So I'll show you how that works in this script because this one's more obvious how it works. So I think at the moment our sun should already be pre-selected. Yep. So from there, pretty much all we need to do is run the script. It's going to go and check the distance of every single panel from the sun, feed that back into the open factor parameter with a normalized range. As you can see, it takes a little while for these to run because it's processing a little bit of data into these families. So the larger the facade, the longer it will take your script to execute. And you can see there at the moment, my script is straying from the sun. So the closer it is to the sun in distance, the more closed the facade becomes. I could alternatively take the inverted relationship of that and map this instead. And now the closer it is to the sun, the more open it will be. So this could be more for like a biophilia based building. So you could be looking at a building that responds like a flower. It could be an arboreum, for example, something that actually has plants in it that need sun at the right times of day. But maybe when it's less sunny, they want to close because they may have a, say, a UV light on top of the panels that actually keeps them growing. And you can see there that's the opposite. So basically, the closer to the sun, the more open it is. So that's just an interesting way of looking at it. The final method that I'll show you is what I call by angle of incidence. So what we're going to take is the normal as a vector of every panel along that surface, and we're going to compare that to the vector that would reach that panel from the sun instead. And we're going to normalize it onto a plane because typically the sun comes in at a relatively consistent angle to each panel because it's so far away. But we're going to take its position at least as reference in that case, and then we're going to use these to compare how large the angle is between those two. And the closer that the angle is to the perpendicular, it will either be less or more open in principle. So if I go back to Revit, and we'll just open up that third script. So this is Solar by actor planar. I've called it planar because I'm normalizing the vectors to a single XY plane. So this one's a little bit more complicated. You can more or less ignore this part of the script. I might just turn this on so you can visually see what the script is doing there. So I'll unfreeze and I'll preview these elements. They're basically there just to show us what the vectors look like as lines. So we're taking all our curtain panels, getting their geometry instead, so that we can give them a bounding box. Of that bounding box, we're going to take its centroid, so the center of that bounding box. And the reason we're going to do that is because we want to find the normal of that bounding box's center in relation to a surface. So that's basically going to be the line that points away from the facade at that particular point. So we've had to select our surface in this case, which is a face. So we've already selected that. Again, we've selected our sun. We're taking our sun's location as well and getting the vectors from each of those centers to the sun as well as a list on the side. So we're more or less ending up with two sets of vectors. But what we're doing with the sun's vector, because the normals are flat to xy, we're also doing the same to the vectors coming from the sun. Because obviously the sun's vectors are coming in at an incident angle from our actor. But what we want to do is normalize that to a plane to get the angle of comparison. So we're taking the x and the y component of that vector, but we're fitting a 0 component back to a new set of vectors coming from that. So basically the same vector, but flat instead. And from there, we're taking those two vectors, we're comparing them to get their angle. And again, then we're just normalizing the range of the vectors again. And that's pretty much it. We can also map it to a 90-degree range. This is an example of where I said you can take a known minimum and maximum instead of working with a normalized range. But in this case, I recommend a normalized range makes more sense so that you do get that extreme of open and closed along your facade. And again, we can stray or follow the sun depending which one we plug into our formula. So we would expect a very similar outcome typically from this, but we'll expect it to sort of follow the facade rather than hit a centralized point when it's run. So I believe this should be ready to run. I'll just cross-check my inputs. I believe they should be okay. So the values are all set to go. Cool. This one takes a little bit longer to run because of the vectors sometimes. Typically I find that this one is the more complex method, but it's usually the more appropriate method. And there's obviously more complex ways you can analyze the angle of the sun and the incidence of the sun coming in. This will be more for a design exercise or where you have absolute confidence you can get a position of the sun that makes sense. Otherwise, it's probably better to work with some scripts such as, I'm trying to think of the names of them. There's one called Ladybug that will give you a lot of scripts that relate to the position of sun and weather, and you could use those to get angles instead. So you'll see here laterally the facade is all responding consistently across because I've normalized all the vectors. So really all you're caring about is the XY position of the sun in relation to the building. And you can see that fall off happening here. So at the moment it's straying from the sun. Likewise, I could take this instead and get it to follow the sun alternatively by plugging this in instead. And you'll see the result of that. And you can see those vectors coming up as well because I've actually set some lines up to represent the vectors. So you can see the normals, but also the normalized vectors in relation to the sun's position from each panel. So this is quite a helpful script as well. So you can really see the power of just how dynamic this process can be and how quick it can be to look at many scenarios with very little information required. And you could bring in any facade into this environment and sort of process a Dynamo script. All you need is that sun actor to create a point that they all reference. This one's taking a little bit longer, but I think it's almost finished. I will go back and just show you that random option as well. There you go. And you can see that facade really starting to take effect in relation to the sun. It's actually quite impressive and quite an evocative form that's emerging as a result. So it's quite exciting, some of these scripts to run. And obviously there's a lot of other ways you can build these scripts. I'll just go back to my solar by image and use my randomized function instead. So I'm basically taking a number of random samples, basically 15 by 5, so I want one sample per curtain panel. And from there I can feed these into a divisor just to half the values in principle. So just to save a bit of time, I might just do the pure divide by 2 because it's all random, so you know, who cares what number it's being related to at this point, purely random. Obviously from a design perspective this has little merit, it's just a fun way of getting something quite dynamic in a facade. Maybe something you work on could be random at some point because it might be a mural or a photo mosaic, for example, that you want to jumble. And you see you get like an absolute cacophony of options out of that. But you can see how quick that is to run and just how impressive that can look. And obviously we can really quickly invert that as well. So quite interesting. And you can see how easy this has been to set up. These scripts are not too complicated. They only use, I think, a couple of nodes from Clockwork. And otherwise that's it. So once this finishes, we're almost finished with our series actually. Cool, and you can see the inversion of that. And you can actually cycle through by control setting. So you can really quickly compare options on the fly, which is quite cool. So that's pretty much it actually. So I guess from here it's really just up to you how creative you want to be with your facade by mapping ranges, whether they be images or solar positions or actors. You can see some examples here of just buildings where they've used these in the past. I believe this is from the Samri in South Australia, where they've got curtain panels that have been optimized to the solar angles to optimize the depth and exposure to sun on the glass. I think this is Council House 2 in Melbourne, where they've looked at optimizing the angle of panels, and I believe these ones might actually be kinetic as well, they move. This is, I think, a pavilion from the Winter Olympics, where they actually lifted small rods off of a facade to actually create faces, which is quite interesting. This is totally possible with the image script that I was using before. And also just a building by Jean Nouvel, where he's actually got apertures, very small apertures in his facade that open and close to respond to sunlight during the day. So quite dynamic, and obviously a very micro version of what we've done on a major scale. So thanks for listening. I hope you got something out of the series, and feel free to leave any comments or questions or suggestions for other tutorials down below. And if you like what you're seeing, feel free to follow me and subscribe if you like, and thanks for listening. Bye.